Okay, welcome to the PT revision video for the use of electromagnetic waves in communication. First of all, it's important for us to understand which parts of the electromagnetic spectrum are used in communication. And there's two main sections. The first is radio and microwave, which is used for TV signals, radio signals, and mobile phones. And the reason that it's used is because these signals will travel through the atmosphere, and radio and microwave are not easily absorbed by the atmosphere. They're transmitted by the atmosphere. So it's useful to use them. If you had a signal that was absorbed by the atmosphere, it wouldn't be very good for transmitting to a distant TV aerial. And the other section of the spectrum that's used is the visible and infrared. And those tend to go down optical fibres, so things like fibre broadband use these, and that's because they're not easily absorbed by glass. And the fibres are made of glass. So again, the same thing. You can travel your signal a long distance down the glass without it significantly being absorbed, so it can reach distant homes. Okay. And the point is that what we do is we superimpose the signal onto the electromagnetic wave, and that means we call the electromagnetic wave a carrier wave. Now, the details of how that works are not important for you guys, so don't worry too much about that, but just try to remember that the electromagnetic wave is a carrier wave for the signal. Okay, so we need to know the difference between the two main types of signal, the first of which is analog. And so we've got here a time on the horizontal axis and signal level on the vertical axis. And this signal level could be anything. It could be the volume of an audio signal. It could be the voltage in a wire, anything like that. So signal level is a very general term. And the point about an analog signal is that it can change however you like. It continuously varies. It can take any value and change at any time. There is no restriction on the shape of this signal at all. Okay, so that's analog. Digital is much more restricted. Very often, though, a digital signal will be derived from an original analog signal. So we've got here our dotted yellow analog signal, our original one, and you make a digital signal from that by sampling it at various time intervals. And when we do that, we get something that looks like this. So the digital signal can only take particular levels, right? There are a set number of levels, and really clearly you can see that it changes at very particular and regular time intervals. So that's the key characteristic of the digital signal. It can take certain discrete values, and it can only change at specific times. So this is an example of a quite complicated digital signal because it's got lots of different levels. And what we're going to see is that most digital signals are binary. You can take this quite complicated one which has lots of levels, and you can always turn it into a binary signal with just ones and zeros. And again, the details of how that is done are not really that important for you. So we're going to skip over that and just look at the digital signal itself. So here's our binary digital signal made up of ones and zeros. So the signal is either on, which is a 1, or off, which is a 0. And you know when it's supposed to change, so you can just work out whether it's a 1 or 0 from the signal level. And I've written the signal, the digital code above the signal, okay, here, so you can see how the two match up. So it's very simple, okay, ones or zeros. Now, you might think, well, why do we want to go to this bother of changing our analog signal into a digital one? Well, it's because of what happens during the transmission of the signal, okay? And this is unavoidable. You have noise added to your signal. So on the left, we've got our original signal. We add some noise to it during transmission. There's no choice about that. This noise comes from the environment everywhere around. It's not noise like sound. It is signal noise. So if we're broadcasting a radio wave, this is sort of random radio waves in the environment that we can't avoid, produced by lots of different things. Power lines produce them, lightning strikes produce them. So, and what happens is they add or subtract from the original signal. So there's our original signal again in yellow, and after it's been transmitted, it'll pick up noise and it'll look slightly different, okay? And sometimes there's lots of noise and sometimes there's not much, but it always changes the original signal. So the red line is now our noisy signal. The point here is that in this analog transmission, we can't tell the difference between the noise and the signal. There's no way to separate the signal and the noise once it's been transmitted and received. So your TV station will transmit the thing on the left, the white line, right? And your TV aerial will pick up that plus the noise, so the red line. And it's got no way of telling what the noise is, how to get rid of it. So analog TV transmissions used to always look slightly fuzzy. They looked okay because they were roughly right, but you couldn't get exactly perfect picture quality unless you had zero noise, which is impossible. Okay, so That's during analog transmission. The same thing happens during digital transmission. Digital transmission is not magic, okay? It's just all we've done is chosen the signal levels and chosen the times it can change at. So it still picks up the noise. So our digital signal, after it's been transmitted, in the same way, you've got the yellow original, and it's noisy, the red line, okay? The point here, though, is because we know that it's supposed to be a 0 or a 1, and because we know how often it's supposed to change, you can design some fancy electronics that will get back the original signal, that will remove that noise, because it can say, well, that's roughly close to 1, so it must be the 1. This is roughly close to 0, so it must be the 0. And your electronics can do that for you. And if you look, you can see now that on the left here, we have our original signal. On the right, we have our adapted signal, our reprocessed signal, our cleaned up one, and they are identical, right? So, in other words, we've overcome the noise. Okay, so processing the noisy digital signal can reproduce exactly the original signal, provided the noise isn't too bad. If it gets really horrendous, and the red line goes a very long way away from the yellow, then the electronics can't do their job, and that's what happens when you have your digital TV picture sort of freeze. That means the electronics have not been able to get rid of the noise. Okay, so what are the advantages then of digital over analog? Well, we've just discussed the one that you can remove the noise from digital signals, okay? And also digital signals work very well with computing because computers naturally store information in a binary format, okay, in ones and zeros. So you can store and process digital information in computers. Processing means things like, changing the brightness of your pictures on Photoshop or changing the colours slightly, colour balance, so you can get a nicer looking picture. That's the sort of thing we mean by processing, and it's very easy to do that with digital information. You would have to convert it from analog to digital first if you were trying to work with an analog system. Okay, so those are the two key advantages. The disadvantage is that whenever you sample your signal, so whenever you produce your digital signal from your analog, it's never exactly what you had to start with. But you can get it as close as you like, and the way you do it is by using more information. So when we're talking about this, we have to know the terminology, right? That each one of these ones and zeros in our digital signal is called a bit, and a collection of 8 of them together is called a byte. And if you want your digital signal to be as close as possible to the original analog one that you've taken it from, then you just need to use more bits per second or more bytes every second to sample it. Okay, if you do that, you can get your digital signal as close as you like to the analog one and still retain the ability to remove the noise from it. So it's just a question, you've got to pay, right? You've got to pay in terms of what we call bandwidth, which is how fast the information is transmitted, how many bytes or bits per second, to get your digital signal close to the analog one. Some of you might be familiar with this from MP3s. When you encode an MP3, you can choose the bit rate. Okay, so you can go into the menus and choose the bit rate. And the higher bit rate you choose, number of bits per second, the closer to the original the MP3 sounds. Okay, so you can get what's called better quality from that. So if you want better quality in your digital signal, you need to use a higher bit rate. So more information every second, more bytes per second. Okay, and that's it.